Thanks. Morning, everyone. So maybe, we know the reason it's so sparse this morning. It's what I discovered yesterday night, that my talk is listed with this title on the abstract book. So that made me pretty scared, because I thought, if organizers invite you somewhere and they ask you to talk about something, you should talk about it, right? So but then I remembered that Scott reminded us yesterday that in Israel you should get to the point quickly. So, I'll...
This is not the correct title? Oh.
I'll skip the preliminaries and get to the point. But don't be too disappointed. The next talk is going to be about the preliminaries.
The order is reversed.
Right.
It's corrected already.
So it's corrected in some places, but not in the printed abstract. So I'll keep that as a souvenir, claim that I talked about Majorana fermions. But no, really, I want to talk about some questions that have to do with the complexity of entanglement, in particular the complexity of the kind of distributions that you can generate by measuring entangled systems. So I'll start, let me start a little bit broadly by saying something that's been said over and over again already in this conference, that entanglement is a very complex phenomenon. We're all...
What was this picture?
Oh, entanglement,
Yeah, but
Magritte?
oh, it's Margit.
Yeah.
And it's called entanglement?
Sorry?
This is the title, official title, entanglement?
No. I think it's called Lovers, something like that. It's actually a series of pictures, and they progressively take their masks out. But right. No, you missed the one joke of my talk, so it's over now. You can leave. Right, exactly. Yeah. Sorry, I can't do it again. So, all right, let's get going. So, so I think we're all familiar with entanglement, and it's as a very complex phenomenon, right? If quantum states require exponentially many bits to be described, if they have exponentially many degrees of freedom, it's because of entanglement. And we know that's not only a generic phenomenon that arises in arbitrary states or random states, but also many states that at least to some extent occur in nature, such as ground states of simple local Hamiltonians. Even these states exhibit very complex patterns of entanglement. So on the one hand, we have this complexity, but on the other hand, we also know that entanglement has to satisfy a lot of constraints. So we know how to measure it using measures of entropy, the von Neumann entropy or the Schmidt rank or things like that. And these entropy measures have to satisfy certain constraints, for example, subadditivity, other types of constraints. We also know that although entanglement is kind of nice when it's in between two systems, as soon as you study entanglement in between three or more systems, it tends to have somewhat of a more rigid structure. So there's this kind of conflict in between generic complexity and structure that is there. And the point is that we don't get to see entanglement, right? It's not something that you can see. The only access that we have to entanglement is through measurements, through experiments that we make, through the classical data that we collect. And the sort of general scientific question is, based on the classic data that we've collected, what kind of picture can we build, can we infer from the underlying physical system? This is what we're trying to do in general. So let me phrase it a tiny bit more precisely. So what's the setup for this talk is that we have a certain number of quantum mechanical systems. Sorry, I keep pressing the wrong buttons. Two or more. There's three quantum mechanical systems, and there's different amounts of a priori information that we can have about these systems. So for example, we could know them completely but implicitly. We could have a full description of the Hamiltonian of the system, and we know that this is the ground state, but we don't have the explicit description of the ground state. We just know it's the ground state of the Hamiltonian. Or we could have partial information. For example, we know that these are bounded dimension systems. This is a qubit, this is a qubit, and this is all that we know a priori about our system. Or it could be that we don't know anything. And, this is the kind of setting you'd have if you study this in a cryptographic setting, where you'd imagine some of these systems might be the systems of your adversary, and you don't know anything about them a priori. The second thing that we're going to do is perform observations on these systems. And again, here there's different levels of a priori information we might have. So for example, we might know what measurement we're performing, right? We know that this is a measurement in the x basis because, this is what this is supposed to be doing. But maybe also we don't quite know what is the measurement that we're making, maybe because we don't fully trust the grad student who made up this apparatus here, or maybe because, again, we're in an adversarial setting, cryptography, Or say we're studying Bell inequality violations, and in this kind of setting we're trying to mathematically optimize over all possible measurements. So there's no a priori limitation on the kind of measurements that you could make. And now we're an experimenter, a classical being sitting there on the outside, and we're observing these systems. So we're making choices of inputs, choices of measurements, and observing the outcomes of these measurements. And the question is, based on these observations, what do they reveal about the underlying physical system? So I'm going to look at this question in the completely unknown scenario. So there's no a priori bounds on the dimension of the system, no a priori information, apart from the fact that they're isolated systems. And same thing for the measurements, no a priori information on the measurements that are being performed on the systems. The only thing we have is the classical data that's collected. So we're going to study this question using a particular language of games. It's just the same question but different language. So instead of calling this guy the experimenter, I'll call him the referee. And the quantum systems, I'll call them players. So the referee interacts with the players through a game. So he sends them questions. So that's what were inputs before, choices of measurements. The players make measurements, whatever measurement they want on their systems. And then they report the outcomes, the outputs to the referee. So I'll call these answers now. And then the referee has a criterion according to which he accepts or rejects the answers that he received based on the questions that he sent to the players. So the nice thing about formulating things in this way is that there's a single quantity, single number that you can associate to any game, which is the maximum probability with which any players or any quantum systems and any measurements on these systems can produce outcomes or answers that satisfy the referee's criterion. So this is a quantity I'll call the value, the entangled value of the game. It's denoted like this. And it captures many different things of interest. So for example, if you're given a game, and you're asking, okay, does this game have a large value? Then you're asking, okay, do the correlations that the experimenter is checking for, are these correlations achievable using quantum mechanics? If they are, then there's a strategy for the players that makes the referee happy and the value of the game is large. On the other hand, if the value of the game is small, then it means that the referee is checking for something that's impossible, even using quantum mechanics, right? It's impossible to achieve these correlations. So this is a question that we want to ask in general, and for those of you who are familiar with Bell inequalities, it's the question that you ask directly when you study Bell inequalities. You have Bell inequalities in games are just the same thing, and you have a game and you're asking, is the value large or is the value small? Are the correlations feasible or are the correlations not feasible? The question that I want to ask is sort of the meta question that we should be asking before asking that particular question, which is, okay, how difficult is this problem going to be in terms of computational complexity? So you're given a game, you want to determine what is the value of the game, what is the best or given correlations, can quantum mechanics produce these correlations or not? So how hard is it going to be to study that? How hard is that question computationally? So let me give you an example to make things concrete. So I was going to call this example, the CHSH game, I almost called it trivial example. And then I went to the RAM session yesterday and facing the sort of, maybe abysmal performance of some of us in the RAM session. I hope many of you were here in the RAM session. So I decided to rename this slide, insert one more slide. So sorry for the delay, those of you who know that, but I'll rename that tutorial, How to Demonstrate Quantum Weirdness. And we have a guest participant, Eddie. So Eddie, this is for you, pay attention. So here's how you do it. So this is just going to be an example of a game. So usually, you have the referee and you have the players. For the purposes of the tutorial, they're usually called Alice and Bob, but today we'll have Eddie. And then the chairman, Umesh, who also seems to be interested in what are the possibilities of untrusted quantum devices. So, okay, so let's play this game. So it's a very simple game. The referee picks just random bits that he sends, one of them to Umesh, the other to Eddie. Each of them sees the bit that they were received. This is the question. And they have to produce an answer, which again is just a bit. And what are they trying to achieve? They're trying to satisfy this condition here. The parity of the bits that they answer should be equal to the AND of the bits that they were sent. So basically this is saying that they always have to answer the same bit, except if the questions they were sent are both 1, right? In which case the answers should be different. So I'm sure many of you have seen this, maybe in terms of CHSH inequality, so just don't worry about this, but that's usually the way it's presented. These are the correlations, just to make the connection of what I was saying before, these are the correlations that this game is checking. Maximizing your strategy in that game is the same as trying to maximize this expression where A0, A1 are the observables, Umesh's observables, A1, B0, B1 are Eddie's observables. Okay, so Eddie, are you ready? Okay, so suppose you're not given any entanglement, you're playing this classically, right? How well can you do? What's the best success probability that you can achieve in the game? You know, okay. Everyone knows the answer. What's the answer? Okay, good. So that's not too hard, right? And you know, I'm allowing pretty general strategies. They can meet beforehand, decide on some secrets, etc. But the point is that once the game starts, say Eddie receives a 1 on his question, he doesn't know if Umesh got a 0 or a 1, so he doesn't know if he's trying to achieve parity 0 or 1. That's what makes it hard. If you just look at this more closely, you realize that the best they can do is just answer 0 all the time. If you answer 0 all the time, you do this 3/4 success probability. Okay, now for the fun part. Sorry, nothing happened? All right, so the point is that using quantum mechanics, using just an EPR pair, you can achieve a higher success probability, cos squared pi over 8, 85%. So that's what you have to tell your friends to impress them. And now, Eddie, I know you don't know how to achieve this, right? Do you? Because yesterday you looked a little confused.
Okay, no, I'll be confused.
Okay, so let me show you how you can do it. I'm sure most of you have seen this, but well, maybe someone here has not seen this, so let me show you, right? How do you achieve 85% success in this game using an EPR pair? So your goal is to satisfy this criterion, and here's how you do it. So Umesh, gets his question, Eddie gets his question, they have to make a measurement in some basis. So I'm going to show you the bases that they use. So first of all, suppose that the question was a 0, then Umesh uses this basis here, and if he gets this outcome, he answers 0, this one 1, and Eddie uses that basis. And if they get input 1, Umesh uses just computational. So Umesh is just computational Hadamard, and Eddie is rotated by pi over 8. So these are the bases that they use. So the point, Eddie, is the bases are not aligned, right? So this is what's buying you something here. You can't win in this game by using aligned bases. So why does this work? Well, so what's the rule here? We're using an EPR pair making these measurements. The measurement rule is going to say that the probability that you get outcomes A and B, given that your questions were X and Y, is the inner product squared between the two corresponding vectors. So we can take an example. For instance, suppose they were both asked the question 0, right? So they're both measuring in the red basis. And what's the probability that they get 0 and 0? It's the inner product squared between these two, which is cos squared pi over 8. The angle is pi over 8 divided by 2. And then these two are also correct, and that's also cos squared pi over 8 by 2. So overall, they're correct if the input is 0, 0 with probability cos squared pi over 8. And actually, whatever the input pair, you can check all the angles. If I didn't mess up the picture, they're always correct, whatever the question, with probability 85%. But that's really because of this rule. I think this is what maybe Umesh was saying yesterday, this cos squared rule. This is where you're gaining something here. Right. Okay. So end of tutorial. Let's get back to interesting questions. So yeah.
If you don't have entanglement there, you said the trick was always to say 0.
That's one way to do best.
Or one of them. But if you try to do exactly the same thing of changing bases, what you would get? Like, what would be the function of the angle?
What do you mean?
So he's saying.
But what are these? I mean, these. So you have bases, but you don't have the EPR pair, right? In the classical.
Yeah, but you do exactly this, and I change the amount of entanglement. It's going to decrease.
Oh, you changed the EPR pair, right? So.
Do exactly the same game.
So you can do the. I guess you can do the calculation, right? You can put two different Schmidt coefficients here. You're saying, and then see what this gives.
Sorry, were you asking what you can do classically?
Classically.
I want to change classically, but I want to do exactly the same
So
protocol that
I think the answer, if you think of it as randomly aligned planes like points, if you were looking for random angles, if it's classical, you get theta, the angle between the two.
So you're
saying you're getting
that
cosine squared theta.
Okay, so instead of cosine squared, it'll be exactly theta.
Exactly.
And
Okay.
And then,
According to some
maximize the
interpretation.
minimum with the classical case.
Sorry.
I think the question is, what is the maximum of the minimum? Here you get 85% no matter what the input you get.
Yes.
And if you do it classically, and this is what you care about.
You can do that. You can get 75% by randomizing.
75% for every.
Yeah, or just by randomizing your strategy, I believe. So you just instead of always answering 0, 0, you probably okay. I think you can. I'm not completely positive. We should check. I think you can make the 75% uniform.
Probably you can represent it by measurement as a race.
Yes. I think that's what Ray's question was. Like, can you sort of interpolate nicely between the two cases? I think you can do that. Yeah. One way to do it would be to parameterize the Bell pair and to have one more parameter here, and as it goes to 0, you should recover the classical.
your strategy depends if you know that it's quantum or classical, but
If you know the state, right?
for example, you're at the cocktail party trying to explain this, you can say change the strategy.
No, so you always need to make measurements in different bases, right? You're always going to have to introduce a basis choice. And I think in his example, you also knew that the states were two completely, where it was an EPR pair, right, or a singlet or something. I think you were, okay.
It can even work out physically if you do it at the correct time. You get exactly.
I agree you want to find a way to say this not drawing the picture, right? And I think this is what you were doing yesterday, maybe. But,
Slightly different.
right, but okay, let's not get into the debate again. Okay. As I was saying, end of tutorial, but I guess it's not. We should have a 1 hour, 2 hour. Next time, 2 hour tutorial.
It's actually not the optimal arrangement. Just
right. Well, actually, so I mean, we're arguing, optimal. So how do we know that this is optimal, right? We know it because we were taught in class, maybe. But this was one EPR pair. That seems really simple. What if I try with two EPR pairs? Well, I can try, but if I don't get anything better, it's not saying that with 3 EPR pairs I wouldn't be able to do better, right? Or what with another state. So that doesn't seem so easy to figure out. In that particular example, so Silson showed that this is the optimal you can do, and it's not, it's not a long proof, but it's not a trivial proof either. There is a proof there, and this is what I kind of want to be looking at. This is basically the question that we're studying in this talk. Is given a game, for example, that game we had before, or some other game, how hard is it to figure out what is the best quantum strategy in the game? So the game, you can think of it as a game if you're happy with that, or you can think of it, as I was saying before, as a set of target correlations that you're trying to reproduce using measurements on isolated quantum systems. And the value of the game is just the best, best score that you can get in terms of reproducing these correlations. So a priori, it does seem like it should be a hard problem, right? Because this is what I was saying just before. If you want to figure out the best quantum strategy, you have to optimize over all possible states, all possible measurements. And as soon as you don't bound the dimension of these states and these measurements, you're facing an infinite problem. And this is a problem that's faced in practice. People have been studying Bell inequalities for 70 years, 80 years, and there's some very simple ones. This I3322 is, you can think of it as a game, 3 questions, 2 answers. We don't know what is the value. It looks like this. It's simple expression, don't worry about it, but we don't know what what the value is for that particular inequality. So it seems like it's a hard problem. On the other hand, yeah, so that's not proven.
Strictly speaking, it's not proven, but we have got quite strong argument that it is.
Numerical, yeah, that's true. So right, there's indication that for this you might need to go to infinite dimensions.
Strong indication, it's not a mathematical proof, I agree.
Okay.
It looks a little bit like the Shannon capacity problem.
Oh my. Let's move on. oh, you mean, sorry, I thought you were talking about the inequality. Yeah, you're right. Yeah, you're right. Yes, for sure. Yeah. And maybe I can say right away that it's exactly computing this number is not known to be decidable. So, or it's not known to be computable. Sorry, because of similar.
I mean, maybe it's worth saying that approximating just the classical value of the game is already an NP.
Right. I was going to get to that afterwards, but yeah, you're right. No, good point. Good point. Yeah. I just didn't. Yeah. But then there's also some non-trivial algorithms. So there's some subtle things that you can do that point in the other direction. For example, for the case of so-called XOR games, the games CHSH that I gave you, this is an XOR game in which just the answers in the game are bits and you take the parity. So this is, in terms of Bell inequalities, is correlation inequalities. For these, there's an algorithm. There's a polynomial time algorithm given a description, explicit description of the game, just a table of what are the valid answers with respect for every pair of questions. There's a polynomial time algorithm that exactly computes the entangled value. And it's based on an optimization technique called semi-definite programming, a generalization of linear programming. So you can solve these SDPs in polynomial time. It's a completely non-trivial algorithm. And that algorithm extends to other classes of games, for example, unique games. I'm not going to get into it, but for those also we have non-trivial algorithms. In the general case, there's something called a semi-definite programming hierarchy. So you have a sequence of semi-definite programs, optimization problems of larger and larger size, such that as you progress in this hierarchy and solve the SDPs, you get better and better upper bounds on the entangled value of the game. The problem is you don't know how far you need to go in the hierarchy in order to get a good bound. So in the general case, there's no algorithm. And so the result that I wanted to present is a hardness result. So it's a fairly strong hardness of approximation result for the game. So it's saying that even given a pretty simple game, so 3-player game, XOR game, so the answers are just bits, you take the parity of these bits, then it's an NP-hard problem to make the difference between the entangled value between slightly above a half or very close to 1. So even very rough approximation, you can think of it in this way, deciding whether 3 or more quantum mechanical systems can, even very roughly generate certain correlations. This is a computationally intractable problem. It's NP hard. It's as hard as deciding, satisfiability of 3-set formulas. So that formulation is optimal in a couple ways. The first thing is, why between these two numbers? Well, because it's an XOR game, if you just consider a strategy that outputs random bits all the time, this is going to achieve success 0.5. So you always know that this number is above at least 0.5. And this is saying that, well, this is the best you can know in general. Like in the worst case, you won't be able to have any more information than it being larger than 0.5, unless you're solving some NP-hard problem. And the other thing is that there's this 3-player restriction. I'll get back to that a little bit later. But as I said in the previous slide, if the case for 2 players and this XOR criterion, we have a polynomial time algorithm. So if I want to talk about XOR games, I need 3 players. So I'm going to explain this a little bit in the remainder of the talk, how we arrive at proving such a thing. I just want to mention briefly that it's building upon some previous work, Ito, Kobayashi, Matsumoto, Kempe, and myself that had slightly weaker results.
This is the quantum game.
Yes.
Classical.
No, quantum. I'm going to talk about classical a little later, but so as soon as there's a star, it means I'm talking about quantum strategies. Later, the star will disappear, and then it'll be classical. But the star is entanglement, no star is.
Classical is easier than the quantum?
No, they're incomparable in general. That's a good question. Let's have this question again if I forget to get back to in 2 slides.
So what's your picture or guest picture about the 2-player non-XOR games?
That's an open question. We'll do that in the last slide. I don't know. It's a good question. But once I explain how I'm using 3 players, then we can get back to your question. But it's true. Open question is what if you have 2 players, but not as restricted as XOR. This I don't know. Yeah. Thanks. All right. Well, that's the outline. So I just want to. So here is where I'll mention the classical setting, because these questions I've been asking in a case where there's no entanglement in the classical setting, as Scott pointed out, the answers are known exactly. So I'll explain a little bit what is the connection between these games and proving hardness, constraint satisfaction problems. And then I'll get into the result with respect to entanglement, and that will involve telling you a little bit about monogamy and exploiting monogamy. And this is where the 3 players will come in. So I'll get to that later. So our goal is to prove this, right? So let me first explain the connection that you have between games and constraint satisfaction problems. This is going to be the fundamental connection that we try to explode here. I'll explain it using one more example. So bear with me. This one is a little bit more interesting than the CHSH game. Maybe not everyone has seen the Magic Square game, another game. So here's the game. So there's the square. This is an imaginary square. It has 9 entries, and your goal is to fill in each of the 9 entries of the square with plus minus 1 numbers, such that certain constraints are satisfied. So what are the constraints? In every column, the product of the entries should be plus 1, and in every row, the product of the entries should evaluate to minus 1. All right, so let's try to do this, right? So first column, this is correct. I'm good. I'm good. Now I have to watch out for the rows. This is good. This is good. And now I'm stuck, right? I can't fill in this entry, satisfy both constraints. And maybe most of you can see already, this is not just me, being bad at filling in magic squares. There's a reason for that. It's impossible, right? Because the column constraints are saying that the product of all the entries should be plus 1, and the row constraints are saying that the product of all the entries should be minus 1. You just can't satisfy both. So it's impossible to satisfy these constraints. Still, let's make the square into a game. So we have our referee, the players, and the game proceeds as follows. The referee picks one of the 6 constraints at random. For example, he picks second column, and he asks Alice about it. And then he picks one of the 3 entries that are part of that constraint at random and asks Bob about it. And the players have to answer with an assignment of values to the variables they were asked about, such that, well, first of all, Alice's answers should satisfy the constraint, and second, Bob's answer should be consistent with Alice's question. The point is that Bob doesn't know which question Alice was asked about, and Alice doesn't know conversely, right? So I claim that the best success probability with which you can win in this game classically is 17 over 18. So 17 over 18 doesn't matter. The point is that it's less than 1. And the reason it's less than 1 is because the system of constraints was not satisfiable. So I don't know if everyone can see this. Let's think about what's a strategy for the players in this game. It's just a table of answers, right? A classical strategy, for example, for Bob, is, well, for every question, what do you answer? So I can write it as a table here. So Bob in mind must have an assignment to all the entries of the square. Alice is the same, except she can be asked one of 6 possible questions, right? Either the columns or the rows. And for each question, she has an assignment of values in mind. And if she wants to win, she better satisfy all the constraints. And here she satisfies all the constraints. But then if they have to be consistent, then they can't be consistent, sorry, because if Alice satisfies all the constraints, there's no assignment that satisfies all of them. So she can't have a consistent assignment. Bob just has an assignment. So they must be inconsistent somewhere, and I pointed out in red where they're being inconsistent. Bob is claiming that when he's asked x9, he says 1. But Alice here, this is the answer she gives to x9. So they can't win in the game with probability 1. So you have this very nice correspondence. This is something you can do generally. I did it for the magic square. In general, you could imagine starting with any constraint satisfaction problem, 3-stat formula, and you play the same game. Pick a clause at random, ask Alice about it, a variable at random, ask Bob about it. If the formula is not satisfiable, the game is not winnable with probability 1, and conversely. So this is how, in the classical setting, you can prove that computing or approximating the value of these games is an NP-hard problem. Let me walk you through this briefly. So I showed you this correspondence here. And what we have immediately is that deciding whether there's a perfect classical winning strategy, so no star, classical strategies, or the best you can do using classical strategies is less than 1. This is just as hard as deciding satisfiability of 3-stat formulas because of this correspondence. So it's an NP-hard problem. Moreover, if you look at this a little bit more closely, you can get a quantitative relation. It's not only, you know, less than 1 equivalent to less than 1, but if the best you can satisfy your formula is, say, 90% of the clauses, then you're not going to be able to win this game with probability larger than 90% or something like that. The numbers don't translate exactly, but you have a correspondence. Now, the PCP theorem, the classical theorem of the 90s, very important theorem in complexity theory, says that if you're given, for example, a 3-stat formula, deciding whether the formula is completely satisfiable, or at most 90% of the clauses are satisfiable, that's the best you can do, that's still an NP-hard problem. And so because of this correspondence, we immediately get that approximating the classical value of the game within here 10% is an NP-hard problem. And then you can, you know, amplify this using parallel repetition, and you get that approximating the value of the game within any constant factor is an NP-hard problem. So that's known, and that's known since the late 90s, and it's known even for very specific classes of games, including 2-player XOR games, where here the constant is not any constant, it's some specific constant. So basically what we're trying to do is to carry this program over to the quantum setting, right? We have, you know, exactly the same, we can do exactly the same thing and see, you know, does this work out? Can we show a hardness of the entangled value? And everything rests on this correspondence between constraint satisfaction problems and success probabilities in the game. So let's get back to our example. This is a, sorry, it's confusing slide. We say exactly same slide as before. Classical strategies. I'm just going to make one tiny modification, which is to allow the players to use quantum mechanics. So now they get an arbitrary quantum state, as we had before, and they can make arbitrary measurements. How well can they play in this game using their quantum state? So it turns out that you can win the magic square game with probability 1 using just 2 EPR pairs, a very simple strategy. This one I'm not going to show to you, but it's very cute. So what this is showing is that the correspondence we had before has completely broken down, because the system of constraints, the magic square, is exactly the same as before. I mean, I can't satisfy the constraints in this square now as I could not before. But still, there is a quantum strategy that wins in the game with probability 1. So the constraint satisfaction problem being hard is no indication that the quantum problem is hard. For example, what if you can always win all games with probability 1? Then that's not hard to compute the entangled value in that case, right? So we know it's not the case, but still. So what we're going to try to do in the remainder, how much time do I have, by the way? Because 10 minutes? 10-ish minutes? Okay. So the whole goal in showing hardness for the entangled value is to restore this connection between unsatisfiability of the underlying system of constraints and there not being any strategy that can succeed in the game with probability 1. This is something that breaks down by itself, and we have to do something in order to restore it. If we restore it, then we'll have obtained hardness as we did in the classical case. So let's see how we can do this, and we're going to use monogamy in order to do that. So let me tell you a little bit about monogamy and why it's going to...
What you wanted to know again?
Oh yeah, I want to prove the theorem. So we have a theorem here for the classical value. This is NP-hard, you know, and it built on this. And now I want to prove the same theorem, but for the entangled value, right? Show that it's also hard to compute or let's approximate the entangled value of a game. So I try to carry out the exact same program. So I have some hard problems that I can start with, right? I have 3-stat, all these problems. These I know are hard. I'm trying to transform a 3-sat problem into a game such that, if the 3-sat is satisfiable, you can win the game. If the 3-sat is not satisfiable, you can't win the game. And that will have shown that deciding the value of the game is hard, because if you could decide 3-sat. This is what we did here. Now, I tried to do it in the quantum setting, and I got stuck at the first step, because I started with a system of constraints that was not satisfiable. I made it into a game in a natural way, but now the quantum players can win with probability 1. So this is something I want to get rid of this basically right now. So this is saying, well, this naive transformation that worked so well classically doesn't work quantum. We have to do something different. So I'm going to tell you.
You want to start with SAT, the classical SAT, and you want to translate it to,
Yeah, for example.
to an entangled game,
Yeah.
such that computing the value of the entangled game is still
No, just so that I can show that if the formula was satisfiable, the entangled value of the game will be 1. That's usually straightforward. The hard part will be to show that if the formula is not satisfiable, then the entangled value is at most 0.9, right? And then,
Probably,
so I'm not going to show all the steps of this, but that's the program, the general
probably you
program.
can just write 1 instead of 1.
Thanks, Gil. All right. So let's do something to try to make progress, right? So monogamy, most of you have heard of it maybe before. I mean, it's really the intuitive thing, right? It's monogamy of entanglement, or a general monogamy of non-local correlations. It's saying that these strong correlations that you get out of entanglement that let you win in games such as the CHSH game with high success probability, these correlations tend to be monogamous in the sense that if you try to obtain similarly strong correlations across not 2 but 3 or more systems, they tend to be weaker in a certain sense. So there's many different ways in which you can measure this weakening. Let me show you a particular way that involves games. So let's take the magic square game again, same game, and I'm going to make a trivial modification to it. Instead of playing this game with 2 players, as we were doing before, I'm going to play it with 3 players. So I'm just splitting up the second player and saying, well, now there's 2 Bobs, Bob 1 and Bob 2. But I play the same game, meaning that I pick a constraint at random and send it to Alice. Same as before, she has to reply answers. Now I pick a variable at random inside that constraint, and now I have 2 Bobs to ask it to. So I pick one of the Bobs at random and ask the question to that Bob. Either the first one or the second one. Not both of them, just one of them that I chose at random. And then I make the same checks as before. So if you think about this classically, this is a trivial change. If you could win the game before with a certain success probability, you can win this game with the same success probability. You just have Bob prime answer in the same way as Bob does. And if Alice and Bob won before, Alice, Bob, and Bob prime are going to win now. Same thing. So classical winning probability of this game is 75%. Things have not changed. No. So right, this circle represents blowing up the original Bob, but no. So I have 3 isolated quantum systems, and I've defined the game. And the question, 75%, 17/18. And the question is, how well can you play in this game using quantum mechanics, but 3 systems? And the answer is, I don't know actually what's the exact value, but it's less than 1. You cannot win this game perfectly anymore because of the 3 systems. Intuitively, what's hard now is that before, how did Alice and Bob succeed with probability 1? They were sharing these EPR pairs, right? And now they're playing this game, and Alice can share EPR pairs with Bob and EPR pairs with Bob prime, that's fine. But then when she gets her question, she has to measure, and which EPR pairs does she measure? The ones with Bob or the ones with Bob prime? Because she doesn't know who she's trying to correlate with. And that's what makes it hard for, that's the intuition for what it makes it hard for her. Of course, she could make a general measurement on the 4 half of EPR pairs, and you have to show that this is not going to let you win in the game of probability 1, right? But you can show it. So that's a significant limitation. I mean, we've achieved exactly what we wanted to achieve for the case of the magic square game. The problem is that it doesn't scale very well. So you can ignore this. I mean, in general, monogamy is studied through entanglement measures. Entanglement measures usually require you to have bounds on the dimension of the Hilbert spaces. Here we have no bounds on the dimension, so we can't use traditional measures of entanglement or monogamy in order to study the problem. But the main problem that we have is that this strategy of splitting up Bob doesn't scale well to larger games that are the kind of games that we'd get by encoding 3-sat formulas. Sorry, yeah, so entanglement can be arbitrary, any generic, any state, any tripartite state. But I wanted just to show you this picture, maybe ignore these, it's not so important. I want to show you this picture. This is basically, if you want to scale this up, this is what you have to do. You take a game, just not a simple finite game like the magic square game, but a family of games in order for this phenomenon to manifest itself, the way it was studied in the previous slide, what you have to do is split up Bob into many, many, many different systems, basically as many systems as he could be receiving questions. Previous slide is not exactly what I got, but this is what you do. So if you do this, then this works out fine. The problem is that now you're really talking about games with, asymptotically many Bobs. This is not the question that we set out to study. In particular, for 3-sat form, I mean, you'll have polynomially many Bobs. So.
And then it is hard to separate.
Yeah, then you can do it, right? Yeah, you get a constant separation. In that case, it's not even hard to analyze. If you have as many Bobs as questions, you can really, yeah.
So will it be the same gap as in the classical game?
If you do that, yes, I think so, yes. So you can basically show that if you take a game, and as the number of Bobs increases, the value is going to go down, and I think for number of Bobs exactly equal to number of questions, to Bob, you get exactly the same value. So then there's no more advantage. And so in the remaining 5 minutes, I want to try to give you an idea of how we can achieve the same thing, because this is really what we want to achieve, but not using hundreds of Bobs, just using 2 Bobs as we had before, using 3 systems. This is what we're trying to do. We're trying to achieve the same result in terms of exploiting monogamy, but not in the naive way as saying that, okay, if I distribute entanglement across so many systems, then it weakens it. I want to keep a small number of systems, have the same kind of weakening of entanglement.
So we started late, so closer to 10 than 5. If you want
Okay, but I don't want to abuse my audience, but I'll take 6 maybe, or 5. So this we're going to achieve using something that I think Umesh mentioned at the end of his talk. It's something that's been introduced in the classical literature in proving this PCP theorem that I mentioned before, called the linearity test. So it's something very useful by itself. I'm going to describe it to you just as a separate element, and then we'll see how we apply it to our particular setting. Right, so for like 4 minutes, you can forget everything that we've been doing. Just focus on this beautiful test, and then we'll plug it back in. So what's the idea? Well, so imagine that you're given access to a function. It looks like this, and you ask to determine if it's a linear function or not. Okay, so everyone can tell, right? This is not a linear function. There's this angle in there. That's pretty straightforward. Now imagine that you don't get to see the whole function, but you're only given local access, meaning you can query the value of the function at specific points, and you're trying to determine whether it's linear or not by making the fewest possible number of queries. So maybe you query it here, you see this, query it here, you see that, and then you're trying to determine if the function is linear or not. So that seems maybe much harder, because, I mean, look, if you make all your queries here, it looks linear.
Do I get a third access?
Yeah, you're going to get a third. If you make all your queries here, you're going to see it's linear, and it seems that only if you query points around here, maybe you'll spot the nonlinearity. But Scott is smarter. He already knows what he's going to do. So Scott, what do? You pick a third point, randomly, make the query, and if the function was linear, you know what its value should be here by interpolation. But if you make the query, you see something different, then you've detected the nonlinearity just by making 3 queries. All right, the question is, does this work in general, right? I mean, it works on my picture. What if I have a ton of angles and the queries somehow manage to work out so that my 3 queries I make are aligned, but the function, has all these angles? So it works. You can do this with only 3 queries, but you have to prove it. This is what Blum-Luby-Rubinfeld did. I'm changing a little bit. Those of you who know their test, it's not usually FP, but just to keep with the picture, I'm doing this over FP. This is just integers mod p. Just remember the picture from the previous slide. So let me phrase that test as a game. Bring us closer to our setting. So we have 3 players, classical players. They have a function in mind. I'm going to query that function. So I ask them, the referee asks them random points, right? So x, y, z. Each of them answers according to the function. I'm assuming, it's not necessary, but for simplicity, I'm assuming they each use the same function. So they're answering A, B, and C, these 3 answers. And then the referee checks this complicated criterion. But what he's checking is that the answers are aligned just as his queries were. He's just checking that the previous picture works out using these ratios here. So that's a game. And the theorem that you can prove about that game is that, well, if you succeed with high probability in the game, then whatever function you've been using, this function must be close to a linear function in the sense that there's 2 coefficients, alpha and beta, so that your function is alpha x plus beta, oops, there's a t missing there, for most of the possible questions x. So I don't know if this is confusing you or not. I mean, one thing that's clear is that it's easy to win in this game, right? Just answer according to a linear function, you win in the game. That's fine. The analysis is saying that it's the only way to win in the game. Whatever you do, whatever function you try to use, in order to win in the game, it must be a linear function.
Or very close to linear.
Or very close to linear, exactly, right. Because you're only, right. So we want to use this. Why do we want to use this? Because this test has the feature that there's a global property, right? Being linear is really something that's global, and we're able to check for the existence of this global property or this global underlying object, the linear function, just by making local queries, making queries at 3 different points. And this is what's happening in the quantum games. We're making queries only local, only checking one constraint and some variables in that constraint. And what we're trying to enforce is that there's an underlying global object, which is a proof, a satisfying assignment. So the linearity test is going to let us sort of restore this connection. So let's try to think about what would be a linearity test with entangled players. So let's play the exact same game as before, but now I have entangled players. So they can apply quantum strategies. When they receive their input x, they make a measurement and they send as answer a, which is the outcome of the measurement. So they have these, my notation, it doesn't really mean anything. They're just making measurements. The question you want to ask is, okay, what are you trying to achieve, right? Before, it was sort of straightforward. I mean, if I have classical players, I can say they're applying a function, and testing that the function is linear, this is clear. Now I have quantum players. They have a quantum state. They have quantum measurements. What do I mean by their measurements being linear? One thing that's useful to keep in mind is here's one thing that the quantum players can do. They can use a GHZ state, or actually you can just think of shared randomness, and they can each make measurements on that GHZ state, and depending on the outcome, they coordinate in order to apply a linear function that's determined by the outcome that they observed. So this kind of strategy will always pass my test, because the 3 answers are always coordinated according to the same linear function. But every time I play it, every time I measure the GHZ state, I get a different linear function. So the statement I had before is not true. There does not exist a linear function that underlies any quantum strategy that wins in this game. This is kind of the obstacle that you have to overcome in order to formulate a quantum version of the linearity test, which I'm going to give you there. So this is just a rephrasement of the lemma that we had before in the classical setting. Suppose the players succeed with high probability, then there exists a linear function such that, well, basically whatever the players do is indistinguishable from the point of view of the referee from players who would answer according to that linear function. Right? This is what I was saying before. Whatever function f they use, if they win, the function f must be linear. Now this GHZ example, or shared randomness, says that if I want to make a statement in the quantum setting, I need to generalize it at least a tiny bit, sorry, ignore this, to allowing distributions. Right? So one thing that's also true is that there could be a distribution on linear functions such that the players are indistinguishable from players who, first sample a linear function jointly according to that distribution and then answer according to the linear function that they sampled. And that's the formulation of the test that we can generalize to the quantum setting. Here's what we can say. If the players are quantum, in general, they apply arbitrary measurements. And so the natural thing to say is that instead of saying there is an underlying distribution, is to say, well, there is a measurement, such that my players are indistinguishable from players who first apply the measurement, get the label of a linear function as outcome of that measurement, and then answer their query according to the linear function. And the strength of the statement is in the fact that this measurement is independent of the questions x, y, and z. So what I've said here is that any quantum players who win in this game must have structure. And what is the structure? The structure is here. There must exist some underlying measurement, doesn't depend on anything. It depends on the original strategies, but it's just a measurement, such that I can replace my players, and I won't see any difference. I replace them by players who get their question, they don't look at it, they make the measurement outputs the label of a linear function, then they look at the question and they apply the linear function. So we've recovered, just from local tests, a global structure, which is this measurement, measurement with outcomes linear functions. Let me just show you on just one picture slide how we use this, get back to the picture that we had before. So what we were saying before is that we have these 2-player games. We had this connection between constraint satisfaction problems and games. And one thing that we did is kind of blow up Bob in this game in order to make it so that if the constraint satisfaction problem we started with was not satisfiable, then the value of the game is not 1. So we had this property that as you have so many Bobs, and this is what Guy was pointing out, if you put enough Bobs, then the entangled value of the new game, where you split them up, is going to become close to the classical value of the game you started with, which we know is connected to the satisfiability of the constraint satisfaction problem. We're going to achieve this now using a much more succinct picture. So here's what we do. We start with the same game. We make it into a 3-player game. And what's the 3-player game going to be? It is not fully rigorous, but just intuitively. I hope this makes sense. What the referee is going to do is, well, he'll pick questions X, Y, as he did in the original game, but he doesn't ask these questions. Instead, what he does is he thinks of them as a line, and he picks 3 random points on the line that goes through the 2 questions he was going to ask before. Don't ask me how do you relate questions to lines. I mean, just think about the picture. And he asks these questions to the 3 provers, these 3 random x prime, y prime, z prime. They have to provide answers, a prime, b prime, c prime. And then he does 2 things. First, he runs this linearity test. Because the 3 questions were aligned, the answers must be aligned. And then, now that he has 3 answers on that line, he performs some kind of interpolation in order to retrieve the answers that the original players would have given to the original questions. Why, can you interpolate? What's the function that you're interpolating? I'm not getting into details, but that's the intuition. So the intuition is that instead of just doing something very naive, splitting one question into the same question sent to many different people, you're splitting it into a smarting way. You're encoding it, distributing it across the 3 different questions. And so what you can show is that this works here. It works almost all the way. Not all the way. The problem with this linearity test is that it's not very efficient. So what you end up doing, if you do this more carefully, is blowing up the alphabet size by a lot. If you had a few questions here, this game is going to have, still as before, exponentially many questions. Sorry, not as before. It's going to have exponentially many questions as there were here. So we've basically traded off, many, many bobs for 2 bobs, but then we've blown up the number of questions. So you have to work a little bit further. But using similar ideas, you can do it, and you can make this into a game that has polynomial size in the size of the original game, based on adapting things that were done in the classical setting that build on this linearity test. And you achieve the same thing as before. Okay, so let me just conclude, summarize. The question we started with was this question, right? Given a set of constraints or correlations, you're asking, does there exist quantum mechanical systems, isolated systems, 2, 3, or more, that produce these correlations? What we saw, is that this is a question that's known to be NP. Answering that question is known to be an NP-complete problem for the case of classical systems as a consequence of the PCP theorem. And what I showed to you is that it's also an NP-hard problem for 3 or more systems. And that was the main statement that we went into. So a couple questions are related to that. One question is, could it be harder? So the fact that determining the classical value of a game is in NP is easy to see, because the witness is going to be optimal strategies. And the strategy is just these tables we had before. You can just send that. In a quantum case, what's the witness? Again, an optimal strategy. How big is that? We don't know. It could be very high dimensional. The entanglement could be infinite dimensional. So there's no natural simple complexity class in which to put this problem. In particular, it could be that it's harder than NP. Maybe this is QMA hard. Maybe you can start with a QMA complete problem, local Hamiltonian, and do the same as before, encode it into a game such that the entangled value captures the satisfiability of the local Hamiltonian problem.
But then it's not even obvious that the problem is in QMA, because you need a bound on the amount of entanglement.
No, it's not right. That's what I was saying. There's no obvious upper bound on this problem. That's why I put QMA hard, because it could be even harder.
Sure.
Yeah. Because there's no upper bound on the dimension that you need in order to play well. The what?
The X part, double X part.
Yeah. But somehow this seems, more.
Sure.
It seems reasonable to me. I mean, another question, so that Dorit brought up, is a very interesting question, is what is the complexity of the problem for 2 systems? There we don't know much. We have these restricted algorithms for XOR games. We have these restricted algorithms for XOR games. Sorry, everyone, we started late. It's not my fault, or it's partially my fault. But you get the conclusion, which is good, or just as good as the whole talk almost. So, so this is a very interesting question. I mean, is it hard? Is it easy? And the technique that I showed you in order to show hardness for the 3-player case does seem to rely on monogamy, right? Some kind of form of monogamy, but it does seem to be using that. Can you find ways to use that in order to show hardness even for 2 players? Or could it be that for 2 players, there's algorithms, the algorithm for XOR games that extends to more complicated classes of games? This is a very it's a question that we should be looking at. It's a very natural question. I don't know what the answer is. I wouldn't even bet on it. Scott, you're going to bet.
No.
Easy or hard?
Complexity for 2 systems?
Yeah.
NP hard, but I'm not putting money on it.
Okay. Damn.
No, Donna has prohibited me from putting money on it.
Okay. And so just to wrap up, the way we showed that is that I showed you a way to use this monogamy that is more robust than the naive way that corresponded to splitting into many, many systems. We introduced this linearity test as a way to express monogamy robustly, as in between three systems only. And what I was saying before is that in order to get the actual result, you need to use things that are a bit more complicated than linearity tests, called low-degree tests, and these kinds of things. Right. Thank you. Yes.
So in the linearity test, you said the standard classical linearity test has to do with there is the standard classical linearity test, and moving to the quantum, you went actually through the probabilistic test,
yes,
where they can actually share randomness.
Yeah.
So. What is basically the difference between moving to the randomness to moving to the quantum? So
there's non-commutativity. It's the difference between diagonal matrices and non-diagonal matrices. So think about what quantum players do. They apply observables, right? I mean, or big measurements. So they're just, big matrices, right? And of course, shared randomness is a special case of quantum. So you can formulate shared randomness just as measuring an EPR pair, but there, always in what Eddie was trying to do yesterday, always in bases that are aligned. And if you use only bases that are aligned, they're simultaneously diagonalizable. So you end up doing analysis with matrices that are diagonal. The
so
quantum case has some, but that doesn't answer. Yeah.
What would be the entire analysis with where you replace entanglement with shared randomness?
Well, no one has ever done that. So you can do it. What do you mean by what would be the analysis? Fourier analysis. Oh, the result would be what I stated. I think I don't understand the question. Sorry.
So if you replace allowing the bobs to be entangled by allowing the bobs to have shared.
Oh, you're talking about this when you have three or more. No, yes, I allow the bobs to use shared randomness. Okay. The result is, there's different ways to answer. The result is the same. The result will be that there exists a distribution such that these bobs are equivalent to using the shared randomness to sample a linear function from that distribution and then answer the queries according to the same function that they sampled. And then if the question is, how do you prove that, there's different ways to prove it. So the classical way to prove it is, maybe
this would help. So, I think the point is that the shared randomness case is already hard, and going from the not shared, the shared randomness case you can solve by just saying, you can, if it works with shared randomness, it also works deterministically, and then you do the usual proof. But if you don't want to do that, it's hard.
Right.
And the first step in what Thomas did was actually to get the shared randomness to work without going for the deterministic case.
Yeah,
that was already a big step.
You're already right. That's a good point. You already get a good flavor of the hardness of the quantum case just by trying to do the classical proof using shared randomness. Because in classical proof, you say you have deterministic functions, and once you have functions, it's good, right? You do Fourier analysis, Boolean analysis. You say things like there exists a large Fourier coefficient. This you can't do here.
Right. So really, my question is: once you do what Umesh said, what is the extra ingredient that you get from looking at entanglement?
So in the case of the linearity test, it's not harder because it's Fourier analysis, which is kind of quadratic. Things work out very nicely. In more complicated settings, what do you mean by what is the extra ingredient? So
Just how much more difficult is it?
You shouldn't ask the person. To me, it's much more difficult, but I don't know.
So probably the answer is several months.
Right. Well, that's a short answer. Yeah. But it's hard to explain because it's due. We can talk about it. Maybe.
Yeah, okay. So one more burning question. Does anybody? Burning?
No, let's have. Sorry, I did you so much harm during this talk. You should be able to. You should be allowed to fight back.
A different question. When you have your result here about NP complete for classical systems using the PCP theorem, but there are things that are hard to approximate because of unique games.
Yes.
So is there any relationship between that boundary and what you're doing?
Say it again. Any relationship between that boundary?
Well, you know, could you?
Yeah. So I guess that's a good question. So there's this conjecture, right? Unigame's conjecture,
Yeah.
which is saying that certain classical constraint satisfaction problems that we don't know are NP hard or not. The conjecture is saying, well, they're hard, right? They're unigames hard or something. So you could say, can you use that conjecture, maybe, for example, to answer that question? Does that because you have a broader range of constraint satisfaction problems to start with, so you have more things to work with. It's a good question. I don't know the answer.
But it's also very relevant that unique games with entangled players are easy.
That's a good point. So, right, Scott is bringing up that if you start with a unique game, which is this particular type of game, and if you just do the naive transformation, the same as I was doing before, actually for unique games, what happened with the magic square is always going to happen. The quantum players will not, they won't do 1, but they do very close to 1, even if the classical was very low. So that's a better answer. The better answer, sorry, is that actually we know that if you do it naively with unique games, it's not going to work.
So unique game is sort of a generalization of this magic square phenomenon.
The magic square is not a unique game, but this phenomenon appears, but it's not 1. You don't get 1. What you have is that it's basically always going to be 1 minus epsilon. It's related to the SDP. It's not always this phenomenon happens, but for hard instances it happens.
I'll ask you later. Thank you.
Yeah.
Yeah, I can also get.
I think he wants to.
Stick that in. Oh, well, now I'm using my own computer. I also have a stick.
Just make sure that. So what?
Yeah, I haven't. Yeah, I actually haven't.